I will explain you theorem number 23.5 in this video. Here you can see the statement. The image of a connected space under a continuous map is connected. This is what the statement. So, I know you can't understand anything from this statement. I will explain you something. After that, you will get an idea about what they are talking about. Okay, so first, they are saying image, continuous map, like all these things, right? So first you have to consider a mapping f from x to y. You have to know something in general, okay? So here this x is a image set. That is, you will say this y as a range set. And here you will have f of x, this f and x, f of x. This f of x is image set. Image set, okay. So here this x is a connected space. Now read the statement. The image of a connected space means what? What they are talking about? Image of the connected space means they are talking about f of x. This x is a connected space, I told you. So, image of the connected space under a continuous map. This f is continuous, okay? They are saying this map, this f is continuous. The image of a connected space under a continuous map is connected. That is, you have to prove this f of x is connected. That is what we are going to prove, okay? So, this statement, they may ask this statement with like in another way also, okay? That is, continuous image of a connected space is continuous, okay? They may ask you questions in both ways. So get ready with both the statements. If they ask any of the statement from these two, you have to know to write the proof of this theorem, okay? So let us start learning the proof of this theorem. Here you can see, let us follow my notes so that we can feel easy. Okay. So you are considering a mapping, that is f from x to y, and this mapping is a continuous mapping. That is what the first sentence you are writing. Let f from x to y be a continuous map. Then what you are writing is, in the second line, what you are writing is, let x, this x is a connected space. In the statement, they are asking us to prove image of a connected space under a continuous map is connected. That is what our statement, right? So here, image of this connected space is what? F of x. So we have to prove this f of x is connected, okay? Okay, that is what in the next line you are writing. Here what you are doing is, you are taking let z equal to f of x. Like that, okay. Let z equal to f of x be an image. This is an image, okay. The image of x is f of x. So here is an image of what? Connected space. Here our connected space is capital X. We know about it. So here let z equal to f of x be an image of a connected space under what? This function f. Okay. That is what you are writing in the third sentence. All these three sentences you are writing from the theorem, from the statement. Now we have to prove this z is connected. This is also you are writing from the statement. Now, since f is continuous, you know that, right? Here you have wrote f is continuous map. So here, since f is continuous, you are going to say in another mapping g is also continuous. Here you have to know something. You are going to form a mapping g from the function f, okay? I will tell you how. In the function f, you are having f from x to y, right? In the function g, in the mapping g, what you are going to do is, you are going to restrict this y to z. That is what you are writing. The map G obtained from F by restricting its range. Range means y, okay? You are restricting its range to what? Restricting it to z. So that you will get G from x to z. Okay? And this mapping will also continuous because you got this mapping from this, right? You got this z by restricting this y. So the conditions that y is satisfying, the same conditions this z will also satisfy. Okay, so that is what you are saying here. F is continuous. Therefore, we are obtaining a map G by restricting the range y to the space z. That will also continuous. Okay. Now what you are writing is, consider a continuous surjective map. Now you got another map, that is G from x to z, right? We know that how we got this map. How we got this map? You have restricted the range set of the mapping F, right? Okay. So here you got a new mapping, that is G from x to z. You know that this G from x to z mapping is continuous because just before you have said that. And you know it is a surjective mapping also. Surjective map means what? This mapping is satisfying the condition on 2. That is why you are calling it a surjective map. So this map is what? Continuous and surjective map. That is what you are writing in this sentence. Now what you will say is, we have to prove what? Z is connected. But here what you are taking is, suppose Z is not connected. It means what? At the end you are going to bring the contradiction. Okay. So suppose Z is not connected means we know. If it is not connected means what? There is a separation of Z. Right? There is a separation of Z. You can say that by the definition, right? So that is what in the next line you are writing. Let Z equal to A union B be a separation of Z. Okay? What you have to write? Let Z equal to A union B be a separation of Z. Here you know that if this is a separation of Z means what? You have said it is a separation of Z. It means all the conditions to say separation of Z is satisfying here. That is why you are writing here A and B are non-empty, disjoint, open set is in Z. These are the conditions to say Z as a separation of Z. Okay. Okay. Here that is how you are writing. How you have to write it? Let Z equal to A and B be the separation of Z. Then A and B be the non-empty, disjoint, open set in Z. Is that clear? Now, since you know that G is continuous, so from that you can say G inverse of A and G inverse of B are open in where? X. You have wrote it by the definition of continuous. You will learn about it in our second unit, I think. Second or third unit you will learn. And you are having more theorems regarding continuous. Okay, here G is continuous, so that you can say G inverse of A and G inverse of B are open in X, and C is surjective. From this you can say this same G inverse of A and G inverse of B are non-empty, and then you will find the intersection of G inverse of A and G inverse of B, so that you will get this line. You know that A intersection B is empty because they are disjoint, right? A and B are disjoint. Disjoint means what? When you find the intersection of these two, A and B, you will get empty. There is no elements. That is common in both A and B. So that is why G inverse of empty. Okay. G inverse of empty. So G inverse of empty means empty. Okay. Now you are finding union. When you find the union, you will get this. A union B is Z, right? Here you have A union B is equal to Z. So G inverse of Z means G inverse of Z is here. G inverse of Z means this, okay? So that is why you are writing X. Now you have all the conditions to say G inverse of A and G inverse of B or separation of X is getting satisfied here. Here you have proved one condition and this is another one, this is another and this is another. All the conditions to say G inverse of A and G inverse of B form a separation of X is satisfying here. So that is why you are writing this line. And then therefore G inverse of A and G inverse of B form a separation of X, right? So in X there is a separation. So what you can say? X is not connected because they are separated. X is separated, right? So X is not connected, which is contradiction because you have wrote that what? In this line you are having X is a connected space, right? The second line you have wrote X is connected, but here you got that X is not connected. How is that possible, right? So you are getting contradiction. Our assumption is wrong. What assumption? Z is not connected is wrong. Therefore, Z is connected is proved. Z is connected is proved.